goes off, and then you know there's 5 minutes for question and answers, okay, from your client. Okay.
Right. Hello, everyone. Thank you for coming to this presentation. My name is Addison.
I'm Greg.
Justin.
I'm Michael.
I'm Jillian.
I'm Monica.
And we are the Glass Gurus. So a little bit about our project. Our objective basically was to quantify the weight percent of iron 2+ within Johns Manville's insulation glass at the plant level to be able to correct the glass chemistry in order to keep their production running smoothly. This objective arose because of a couple of problems. The first problem being that iron 2+ absorbs infrared radiation in the form of heat, which can cause an overflow in the production line. And to combat this issue, manganese dioxide is used to convert the iron 2 to iron 3. However, they use molybdenum electrodes for their melters, and when introduced to oxygen at high temperatures, this tends to corrode the melters. So the weight percent of iron 2+ is desired because they can add specific amounts of the manganese dioxide to reduce the damage to the melters. Currently, it takes about 2 to 3 weeks for Johns Manville to get that data because they have to send samples from their production plants to the Littleton headquarters to do wet chemistry analysis. So this stops their production. So our solution uses spectrophotometric methods to get the weight percent of the iron 2.
Right, so just like Addison said, we use spectrophotometry, which involves shining a light beam through a sample, which hits a photodetector to measure the constituent elements that are in that sample. So some of the problems that you can come up with glass is that it has jagged sides, and so the light beam is going to refract off of those sides and miss the photodetector completely. So what we used in our solution was Snell's law for a basis. In order to get that light beam to travel straight through the sample, we submerged the glass in a fluid with the same refractive index as that glass. So that way the light beam travels straight through, it hits the oil at a 90-degree angle following a straight path, then it hits the glass, and because those two have the same refractive index, it keeps that straight path and hits the photodetector, even with jagged surfaces in the glass. And now Monica will talk a little bit about how we actually implemented that.
Correct. So the way we actually decided to go about solving our issue is to develop a procedure instead of reinventing the wheel. Basically, we'll have first the input of all the materials that we gathered, which you will see later, and then there's 7-unit operations that you go through in order to get an actual quantity of iron contained. So you go through all these steps, and then you'll end up with an output. And we actually made a brochure for people to see the procedure that we developed. And to make sure that we met the client requirements, Jill is going to talk about them more specifically.
Yeah, so a couple of our client wishes in the beginning was that, like Adam was talking about, right now the procedure takes 2 to 3 weeks because we have to ship their samples to the headquarters to get tested. But this procedure puts that time down to less than an hour, and it's even less than that. It takes about 20 to 30 minutes, which is a lot less than what JM has to deal with right now. So that's a good requirement. And then it's also a very simple procedure. That was another requirement of ours. We don't want to have to pay for workers to get trained to use fancy technology that they don't have the technical knowledge for. So this procedure is very easy. Any plant level operator would be able to do it. It's also a very safe process. Clove oil is not very hazardous at all. And our last requirement was that it costs less than $50,000 to implement per plant. And we came in at about $19,000 under that. So our process definitely implements all of the requirements that we needed to. And now we will actually show you a little bit about how easy our process is.
Well, because our procedure is so simple, we figured instead of just telling you about it, I'm going to actually perform it for you real quick. So first we have this, our little bag of crushed glass. None of it, they're not uniform pieces, they're just kind of randomly distributed. And I have my blank cuvette here. From here, all I have to do is pour a bit of the glass into the cuvette. Well, that's a big piece, we don't want that one in there. And then, I have the glass in here. I've already pre-measured out 2.5 milliliters of the clove oil. And from here, all you have to do is just pour pour it in. And from here, all we did was put a little bit of parafilm on top, just to ensure that none of it leaks out. And then from here, we have the glass in the cuvette, and all we have to do is put the sample in the spectrometer and simply press start. So and then from the spectrometer would run it and give out some data that will be talked about a little bit later. So as for the quality and construction of the test, we used a Carry 5G UV Vis NIR spectrophotometer, which is the setup that we used in Coors Tech is shown here. It has capabilities of 200 to 3,000 nanometers, but the iron 2 plus peak is around 1,100 nanometers. So we are only analyzing from 800 to 1,500 nanometers. And as for the clove oil, the index of refraction matches within 0.01 of the insulation glass, which is very, very close, but it could always be better, and we'll touch on that a little bit more later. And as for the particle size, we initially thought that the smaller particle sizes would generate better data, but so for that we used a sieve, and we sieved all the glass through to about 0.01 inches, which is pretty tiny. And all the sieved data was actually a lot worse than a larger chunks, so that process changed there. And now I'm gonna pass it off to Michael to talk a little bit more about the computer model and how all that works.
So once a plant operator gets that data from the spectrometer, they can export it as a CSV. And we created this app to be able to analyze and calculate the iron 2 weight percent without having the operator have to do any calculations on their own. So what that looks like is, currently they'll get a CSV that looks like this. We have the app set up to only look at a very narrow type of CSV because we weren't entirely sure what Johns Manville would want to purchase and how they would want to format their files. So with that in mind, right now the operator would only have to delete all these kind of strange parameters that are within the document, and they'll save the CSV, and all they'll have to do is upload that file up, and I think I said soil absorption wrong because I'm silly. I did something weird because
Is it absorbance?
Yeah, absorbance, that's right. So as you can see, right now, just how the model is set up, this can change as it goes forward, but once you upload the CSV, the operator will have access to the spectrometer view graph to see if there's anything strange going on within the data collection method, and as well as this calculated weight percent of the iron 2 plus. So this is using our current computer model, which I'm going to get into now, but also they can look at the values of that data to determine whether or not, if there's something strange going on around 1,200 nanometers, they can diagnose it directly from the app. So with that in mind, talking a little bit more about our computer model that we used. So we created our computer model entirely within the free open source program R, and we exported this data, the R code, using the Shiny web app. This allows us to basically put the R code onto a Shiny server, which is absolutely free for anyone to use, which means that we can distribute it very easily to plants around the world in order to use in the inspection process. So basically, right now the app is set up to use any sort of CSV file. This can be modified further in the app if desired, if something like a text or Excel file is wished to be used. However, this is how it's set up right now. And how we created this mathematically is we did a linear regression of the Beer-Lambert law. So what that looked like is that we basically tried to identify the coefficients that would modify the absorption values in order to calculate that iron 2 plus concentration. In order to validate our model, there's not currently a statistical validation on this standard for doing this type of spectrometer computer model. However, we kind of used ASHRAE Guideline 14, which is a guideline for installation systems and modeling that goes on with energy systems. And we kind of use this as a framework to build out the statistical equations that we need to validate the model. So when we got the data, when we did the testing, we actually noticed that there was this happened. Basically, if you notice that, if you look at this green line here, that should be at the same place on each graph. What we're noticing is there's a large magnitude shift as the iron concentration increases in the overall spectrometer data. So if you notice, the one on the left has a lower iron 2 plus weight percent than the one on the V graph on the right. So So this meant that we couldn't actually look at the specific signal peak for the iron 2 plus at the 1100 nanometers because our signal strength was too small, was much smaller than the noise. But we figured, well, if we noticed that this was actually consistent as a linear regression as we moved up in the iron 2 plus concentration. So we decided to pivot a little bit from using the Beer-Lambert law and use this magnitude shift to predict the iron 2 plus. When we did this, we found that this is what we got. So this is what our linear model looks like right now using the 4 samples that we were given from with known values we were given from Johns Manville. If you notice, as the iron 2 plus concentration increases, the overall magnitude shift also increases in this linear fashion using this equation right here. Now, this is about the calculated error that we got. That error increases as the absorption value gets larger because there's error in this coefficient right here. And also the smaller ends, the procedure also seems to not be as accurate as in the middle there. So what that tells us is that there's an upper and lower limit of how accurate our model is currently, but this will likely change as you add more data points to the model. But how do we know if this is actually a model that's representing the data we have? Well, by doing the statistical validation we mentioned before, we calculated all these statistical terms, and basically what this tells us is that for the number of data points that we have, all of our values except for the y-intercept term in our equation are statistically valid. So now these values should improve as you add more data points. The recommended for the standard is usually around 30 data points in order to isolate outliers and to build out a good statistical framework. However, what this is telling us is that this model does actually seem to show this correlation between the absorption peak, the overall magnitude change, and the weight percent of the iron 2 plus. So this does seem to be a valid way of calculating that out.
So like Michael said, we came up with the linear regression model using those 4 known shown in the black, and then with that, we used it to predict the 2 unknown that are shown in the blue. And later we'll talk with the representatives from Johns Manville to see how close those values actually were. So now that we've gone through the process a little bit, let's talk about how much this costs to implement into plants for Johns Manville. We estimated the cost of about $31,000 per plant, and 99% of this is a one-time upfront cost associated mostly with the spectrophotometer. So we estimated the cost of that piece of equipment to be about $30,000. And this is a high-end spectrophotometer, which we definitely recommend because it's going to produce those reliable, accurate results. As well, in a lab setting and a plant setting, it has a low footprint, so it doesn't take up too much space. And we really believe that this $31,000 is worth it because in the long run, it actually it pans out. It's a little bit cheaper. Each sample, it takes only about less than $10 to run, adding a little bit for labor costs, and then after a few samples, there's a waste disposal associated with about $25. Monica, to wrap it up.
Yeah, so to conclude our semester-long project, we were able to come up with this actual procedure. And just to reiterate, we met the client requirements by making it a procedure that is gonna give you a weight percent of iron. We were also under the budget, so we have like extra money to spend if that was necessary. And it took under an hour, like I said. Though we were able to get an actual result for insulation testing, we weren't able to get it for the insulation glass. We weren't able to test the E-glass. But for that reason, we would need to continue further research, and the process can definitely be developed more. But overall, it was a procedure that was fairly simple. The things that Michael explained were more complex, but it's basically all that the plant person would have to do is drag a file, and we'll actually have a result. So that was a
So moving forward, we recommend that if Johns Manville wishes to continue this project, around 24 more samples and the data for those samples should be put into the linear regression model just to make it more accurate. We also recommend investigating and developing noise-reducing code to highlight and exaggerate the peaks of the iron 2 plus. By doing so, then they can actually use the iron 2 peak at around 1100 nanometers to get more accurate data on the weight percent. To go along with this, more research and testing can be done on the index matching fluid. Currently, we just have the clove oil, and the index of refraction changes for every sample of glass that we have. So it's a little more off than for some than the others. And so solids or liquids, as long as they're miscible with the clove oil, can be mixed in to change that index of refraction to more closely match the glass, which will cause less scattering overall for the spectrometer. And then lastly, we recommend that once finished for the insulation glass, they can modify the step slightly to apply it for the e-glass. And we've made this fairly easy because our typical preparation should be universal at the early stages of production throughout their products. So with that, that concludes our presentation. Does anyone have questions?
Questions with the client? Go ahead.
Could you go back to the slide of that showed the two different absorbances?
Oh yeah, this one,
Keep going,
Oh,
that's
the
the-
graph.
Graph.
the graph, yeah.
That
Keep
one,
going,
one before.
one more. That one.
Perfect.
Could you- So what is the absorbance, it looks like just one number. So is the absorbance at a specific wavelength, or is it some calculation out of that whole curve?
So, yeah, so how we calculated from the model is we looked at the absorbance specifically, the maximum absorbance from 1050 nanometers to 1150 nanometers. So basically, I created we created a subset of that, and we looked at the maximum value of that to calculate using the model.
And then, why clone oil?
So clove oil and the insulation glass both have a refractive index of about 1.53 to 1.54. So since that clove oil matched so closely to the actual insulation glass, we decided to use that. It's also very non-hazardous. It's very similar to like your vegetable oil. Obviously, we use cloves in cooking and all that. So as Monica's going to hand off to you, if you look at the sample, they do match fairly well just from visual inspection. But since that refractive index matched so well, that's why we decided to use clove oil. It's also fairly easy to order through Sigma Aldrich and other chemical companies. So, and there's not really a large waste cost associated with that since it is non-hazardous.
Yeah, and the only reason Greg was wearing gloves and eye protection was because it is an essential oil, which is always a mild irritant. So if you were to get it in your eyes, that would not be good. Or if you were to swallow it, that would not be good. But otherwise, it doesn't cause any harm.
Well, it certainly would be better than like the Cargill index oils that really don't smell very well.
Mhm.
And it could have some other bad things in it. So anyway, very good work, interesting. So for the graphs that you're showing, what's the effect? You said you like big pieces, not little pieces. I mean, is there some kind of guideline to this? Because under Beer's law, it really kind of makes you adjust something for thickness. And so the pieces is kind of hard to judge. What's the thickness of the sample?
So we started with the smaller pieces. They were almost as fine as sand. And we figured that with smaller particle size, it would be able to be mixed up and kind of float around in the solution, so that we originally thought that like big pieces were going to cause more scattering because it's just one big face that would scatter the light. However, since the clove oil didn't match the index of refraction like perfectly, with smaller particles and more surface area, it's caused the scattering to go off the graph. So I think our first couple tests with the smaller particles, the absorption was like way off the graph. You couldn't even see the data. So then we tried with bigger, larger pieces, and since the refraction, or the index of refraction doesn't match it perfectly, it's still, like you can see the glass chunks inside the clove oil, but it made the data a lot less scattered. So ideally, if the clove oil matched the index of refraction for the glass perfectly, the sample size wouldn't matter at all. You could use however large a piece you want, or you could use like super fine particles that are almost like a powder. And since the index of refraction would match perfectly, the light would just go straight through everything and it wouldn't matter at that point. But since we only had the clove oil and we didn't try mixing in any solids or anything, the larger pieces work better for our data.
What would the absorption graph look like for just the oil?
So it would actually look very similar to this. When we ran our tests every time, we did a blank cuvette with just clove oil in it. And this is the peak for the clove oil. And then the rest of this line, whenever we put the glass in, wouldn't change very much. The only change would be in the magnitude, which is why we decided to analyze that.
So that was a single beam instrument, not a dual beam?
It
It was a dual beam instrument. We had a reference frame, which some of the ones we filled, like we did two trials for each one. Some of them, the reference frame included the clove oil, and some of them included just a blank cuvette. We found that the results, I think they worked a little bit better with the blank cuvette in the reference frame rather than the clove oil.
You mean an empty cuvette?
Yes, yes, sir.
Very nice work, thank you.
Good job, guys.
Any other questions from the group?
Do you guys have, they've seen these, they've each seen each other's presentations throughout the semester, so they're probably like, don't have much stuff. Do you have any? else? No? And they're all like, no, we already know this. We saw this before. Yeah, they know each other's projects a little bit. But if you'd like to meet with your team, you know, enrollment in Becca, that's absolutely fun.
Hey, you have a clicker. It's like,
Yeah, feel free to use.